Okay, so what we've been discussing, I just called momentum. Well, now we're going to be more specific. It's really linear momentum, right? Momentum along a straight line. Well, guess what? We spent a lot of time talking about rotational motion, and so if there's linear momentum, it stands to reason that there's also something called angular momentum. And what we're going to see, linear momentum is conserved for an isolated system. We're also going to see that angular momentum is conserved for an isolated system. And there's some really cool demos that go along with that, which I'm not going to do, sorry, but I'll show you some short pictures. Okay, let's just review a little bit first. So F equals ma, and then we learned the rotational version of this equation. So the rotational version of force is torque. The rotational equivalent of mass is rotational inertia, and the rotational equivalent of A is alpha. So I hope you remember that from a few chapters ago. So torque equals I alpha is the rotational version of F equals ma. Now this I, we're going to talk about I, just to remind you. So I is the sum mr squared. So if you have a whole bunch of particles, just mr squared. So I, again, I is like mass. And so if a lot of the mass is located at large R, you can have a large I. So it's going to be hard to accelerate it. So this is usually a pain in the neck to calculate. And so luckily the book has this great table here, and it lists the value of I for these common geometries. And we already discussed that in gory detail, so I'm not going to do it again. Okay, so that's good. Now, there's something new that we need to learn, and that has to do with omega. So omega, if you remember, so velocity, linear velocity is delta x over delta t. Omega is delta theta over delta t. Now, when we learned that, we said v vector equals the displacement, right, over delta t. So, we were pretty happy with vectors here, but we've never talked about vectors here. Well, you'll see why, because it's kind of strange, right? So here's how you figure out the direction of omega. Again, it's kind of strange. So here's a disk, and it's rotating. From my perspective, it's rotating counterclockwise. So just pretend I have a disk, like a turntable, like a pottery wheel or something like that. It's rotating counterclockwise. Now here is the rotation axis. So just pretend I have this disk, this turntable, and here's the rotation axis. So to figure out the direction of omega, I grab it, the axis. It has to be with the right hand, not the left. It has to be with the right hand. So I grab the axis with my right hand. Now here's the important thing. The fingers have to point in the direction of rotation. Okay? So I'm going to grab it like that, right? Because the fingers are in the direction of rotation. The thumb goes like I have here. The thumb is the direction of omega. All right? That's called the right hand rule. So using your right hand, curl your fingers in the direction of the rotation, yeah, with your thumb along the rotation axis. The thumb is then pointing in the direction of omega. Okay, let's say I had a turntable rotating clockwise. So now this is the direction of rotation. So then here's my axis. Now I have to grab it like this, right? So it's clockwise. So I grab it like this because my fingers are in the direction of rotation. My thumb now points down. So omega would point down. Now that's probably weird, but you'll see it makes a lot of sense. All right, just keep the faith. Okay, keep the faith. All right, so there's more than one equation for angular momentum, and we're going to go through them all. So anyway, but okay, so linear momentum, P equals mv. Okay, now let's say we have a symmetrical body, symmetrical rigid body, like a disk. It's symmetrical, right? It's a disk. It's a uniform disk, symmetrical. And let's say it's rotating about its center of gravity. Remember that? In other words, through its center. So for this special case, symmetrical, rigid body rotating about its center of gravity. For that special case, life is really good, as shown on the slide. So this is what I'm talking about. So generally speaking, linear momentum, P equals mv. All right, symmetrical rigid body rotating about center of gravity. L, okay, so whatever reason, angular momentum is represented by uppercase L. I don't know why. Okay, L is angular momentum. Okay, what represents M? Well, I. We know that, I. And then, what's the rotational equivalent of V? Omega. There you go. Okay, so this is the formula for angular momentum, only for this special case, though. But it's nice and easy to remember, because if you know this, bingo, you know that. So it's kind of nice, right? So that's nice. All right. All right, now let's talk about conservation. So okay, so that's Newton's second law in terms of conservation, in terms of momentum, right? The sum of the forces equals delta P over delta T. Okay, so once again, if you're in deep outer space and there's no external forces and you throw something, what's going to happen? What's going to be true about the momentum? It's not going to change, right? It's not going to change because deep outer space, the sum of the forces is 0, so this is 0, so this is 0. So that means delta P is 0. That means P doesn't change because delta means change, right? So if there's no change, it means it doesn't change. Okay. All right, so that sort of makes sense. All right, so if we have an isolated system, sum of the forces is 0, delta T is 0, so P is constant. All right, now guess. I want you to guess. What's the rotational version of this? Okay, what's the rotational version of this equation? Just guess. You'll get it right. I promise you. So let's do it. So sum of the forces equals delta P over delta T. Okay, what's the rotational equivalent of force? Torque. What's the rotational equivalent of P? L. There you go. All right. That's all you had to do. Isn't that great? So, all right. So that's what it is, right? So the sum of the torques equals delta L over delta T. That's the equivalent to this. So this is Newton's second law, you know, in rotational variables. All right. Now, guess what? If you have an isolated system, so the sum of the torques equals 0, of course, that means that delta L over delta T is 0. That means that L doesn't change, right? So there you go. Isolated system, L is constant. All right? So, momentum conservation. That's awesome. Okay, oh boy, this is probably not going to work. Well, okay, so let's cut.